Hello everyone, welcome to my channel and welcome to this video. In this video I'm going to discuss about something which really fascinates me, which has always fascinated me and I really find it interesting, and that is tunnel, or rather network tunnels. So in this video I'm going to create a tunnel, a point-to-point IP tunnel, or rather an IP in IP tunnel from scratch using Linux TUN devices. So in general there are a number of ways using which you can create a IP tunnel. The approach that I'll be taking in this video is using a TUN device in Linux, which is a virtual network device in Linux. And so in short, I'll be creating a IP tunnel or an IP in IP tunnel from scratch in Linux using Linux TUN device. So it might sound a bit mouthful, but do not worry, I'm going to explain each and every step and each and every concept that I'm going to use in this video. So as always, without further delay, let's get started. Okay, before we start building our tunnel using TUN device, let's first try to understand what actually is a tunnel and how it works, right? And why should we be interested in tunnels in the first place? Like, why do we need tunnels in computer networks? Just like a normal physical tunnel connects point A to point B, point A to point B, right? So a physical tunnel is nothing but a path on road from anywhere in it's a path in space from point A to point B. It might be going through a mountain, or it might be going through a tunnel might be going below a bridge, overbridge, or anything like that, right? So the main purpose it solves is connecting one point to another point. So similarly in computer networks, so this is like a physical tunnel, just for the record, and this tunnel can be used by cars, human beings, etc. Just like a physical tunnel, the work of a network tunnel is to connect two nodes, let's say node A to node B, right? And usually it's bidirectional. So like node A can communicate to node B and node B can communicate to node A using a tunnel. But then a network connection between two nodes pretty much does the same thing. Like if you take a LAN wire and connect two computers, or if you take a LAN wire and connect your computer to your router and connect another computer to the same router, you will be able to connect two nodes, right? Or you can connect your mobile phone to your cell phone to your Wi-Fi, and you can connect to other devices and other networks. So what's so special about a network tunnel? So what a computer network tunnel allows you to do is packet encapsulation. And that's like one of the most important things or features provided by a tunnel. What does packet encapsulation mean? So tunnels give you the flexibility to take a packet which is using a particular protocol, let's say protocol A, and encapsulate that packet into another packet which is, let's say, using a protocol B, and send it over a tunnel, right? So if I try to explain it with an example, let's say this tunnel between node A or device A and device B is using, let's say, TCP. So let's say now I have a device A and device B. So what device A and B wants to do is, like, they want to communicate over UDP. And for some reason, let's say you want to encapsulate these UDP packets between device A and device B into TCP packet. So for that reason, what you can do is you can use a TCP tunnel. Now, instead of sending this data directly from DA to DB using UDP packets, what you do is you use this tunnel. You use this tunnel to send the packet over a TCP tunnel. So what happens is this UDP packet gets encapsulated into a TCP packet, and it goes over the tunnel. So in this case, the tunnel is a TCP tunnel, but the actual data is UDP data. So this is a very naive example, and this is also this node A and node B where, let's say, the tunnel software is running. That is also an abstraction. The tunnel software might as well be running on the device itself. So the tunnel is also a server client system or a peer-to-peer system. So the tunnel client might be running in the device itself, and the tunnel server might be running on its own dedicated server, and another device B might also have the tunnel client installed here, and then the tunnel clients can communicate the data over the actual tunnel. So there is a very abstract and simple example of what a tunnel is capable of doing. Again, there are various types of tunnel, but one of the core use case of using a tunnel is packet encapsulation, wherein you can encapsulate a packet using a certain protocol into another packet using a different protocol and transmit it over a tunnel. It could have been pretty much like you are sending a ICMP packet over a TCP tunnel or a UDP tunnel, right? or you could be sending normal UDP packets over a SSH tunnel. In that case, the tunnel is encrypted, right? Because in that case, the tunnel is a secure tunnel and you are sending your data through a secure channel. Which brings us to the next thing, that is categories of tunnel. So there are a number of tunnel categories. There are different kind of tunnels. So a very common type of tunnel which perhaps all of us have used. This example is perhaps the best example to which you might be able to relate, and this perhaps all of us have used at least once for some reason or the other. So let's say there is some content over internet that you might want to use, let's say some TV show or something like that, and let's say it's a OTT platform, or it's any movie platform that you want to access, but that a particular content is blocked in your country or in your location, and you can't access it with your device in location A, which is your area, right? So what do you do in this case? For example, what usually we would do is, a very common solution to this problem would be, somehow you route your traffic to some other device or other server, let's say server or device B, which is located on location B, where that content is available, right? So instead of trying to, let's say this is the content you are trying to watch, like it can be any movie, it can be any TV series, web show, anything like that, and let's say instead of trying to access it from device A directly, which is situated in location A, since this is blocked, what you would do is you would first route your traffic to this device, and from this device then you would want to access this content. Since location B is whitelisted, device B will be able to access this content, and then it will get the content data, or it will stream this content from here all the way back to your device via this device, right? I'm pretty sure you all have guessed it, and in this case what the software that we are using, or kind of tunnel that we are using, is a VPN, virtual private network, right? We are using a VPN tunnel or a secure tunnel. And why this is a secure tunnel? Why do we need secure tunnel for it? Because you don't want your data to be traveling unencrypted across the public internet, right? So this channel that is present between device A and device B, where the VPN server is running, needs to be secured. And from here it can be your normal HTTPS. So what's happening here is, in reality, to a user, what it seems is like device A is making a direct call to the content server, but in actually it's not the case. What the VPN client, so the software running here is the tunnel client, or the VPN client in this case. The VPN client will route all the traffic through this tunnel instead of directly to the content server over public internet. It will route it through this tunnel, and then this VPN server will make a connection to, or route your request to the content server and proxy it back to your device. So that's an example of a secured tunnel. Often the protocol used here is IPsec. A very common VPN is OpenVPN, which is open source and which is pretty common. There is another very common example of VPN tunnel. There is also SSH tunnel, which you can create yourself using SSH port forwarding. One very easy way to create a tunnel. It's a bit slow at times, but yeah, it's a very cool and easy way to use SSH tunneling. Even in that case, you can, what usually happens is, let's say again this is device A, this is device B, and so basically you forward your SSH port to this device, and then whenever you are making any connection to any web server, it goes via this SSH tunnel that gets created to that web content or whatever server you are trying to access. So SSH port forwarding, both local and remote SSH port forwarding, is also a pretty cool way to create tunnels between two devices. And finally, well, I'm giving you only certain examples of tunnel categories. There are various resources on internet from which you can get an exhaustive list of tunnel categories. For example, one very good resource is this page by Cloudflare, where there is a nice explanation of what is tunneling and the different types of tunnel that exists. Okay, so the other category of tunnel that we will be majorly focusing on in this video is IP in IP tunnel, or simply IP tunnels. You can also read about IP tunnels here on this page, and you can also read about them over the internet. There are lots of good resources on them and how to set them up. But here we will be, in this video, we will be setting up IP tunnel from scratch using nothing but features provided by just the Linux kernel. The main use case of IP tunnel is not by default a secure tunnel, but the main use case of using IP tunnels is creating routes that don't actually physically exist, right? These are virtual routes between devices and nodes, and these routes do not actually exist. And I mean, these are not local subnets, but to some extent virtual subnets. What happens is, let's say you have a device D1, which is connected to a local network, and it is exposed to internet via some internet gateway, and let's say it has got an IP 192.168.10.2, right? It's connected to the internet router. This is internet router. Let's say its IP is 192.168.10.1. I mean, it's internal IP. And let's say there is a device D2 which is present on the public internet. It's present on the public internet, and let's say its IP is 172.40.10.2. And so let's say, for example, this IP is a public IP, publicly routable IP. Maybe it's just it's a server. And now what you want to do is, like, let's say you want to create a new route between this device and this device, or this device and some other device which is present inside this internal network, right? This device is, let's say, present internally in this network and it's not publicly exposed, but let's say this edge server, let's consider it's a edge server, or there's some sort of server which has got a public IP attached to it, or maybe it is attached to an internet gateway, right? So let's say you want to communicate to this device or this device over something like a separate subnet altogether. Let's say D1 wants to connect to D2 or D3 over a private subnet which has a range of, let's say, 10.10.8.1/24 subnet, right? So let's say it wants to use this subnet to communicate over D2 or D3, but it's not a local subnet, right? And how would you do that? 10.10.8.1, there is no interface which is right now existing, which is 10.10.8.1/24, and D1, D2, D3 are not even in the same network. D1 can only connect to D3 or D2 over the public internet. So one way to connect would be directly calling 172.40.10.2, like that. I mean, it cannot create a subnet involving this three nodes, D1, D2, D3. And that's where exactly IP and IP tunneling comes into picture. With IP and IP tunneling, you could assign a virtual interface to this node. Let's say you assign an interface to this node 10.10.8.1. You assign another interface to this node 10.10.8.2, and let's say you assign this one something called 10.10.8.3, and let's say you have applications listening at this IP and at different ports like 55551, or another application is listening on this server at 55552, and various applications listening on this IP. So now a client on D1, let's say there is a client C1 which is sitting on this server or this node. Let's say there is an application, we can call it a client application. So let's say a client application is running on device D1, and now let's say it wants to connect to one of devices D2 or D3. So it can simply use this virtual IP or virtual interface IP, and it can simply create a TCP or a UDP connection depending on the application running on D2. It can directly contact the IP 10.10.8. let's say 2, or 10.10.8.3, or any IP that's in 24 and which is a valid IP for these devices where something is running on some particular port on those IPs. C1 can easily contact those IPs and can get back data or whatever it wants to do. So now what we are essentially doing is we are creating a subnet which is completely behaving like a local subnet. Like for C, the client, this 10.10.8.1/24 subnet exactly behaves like a normal local physical subnet, but in reality it's not a physical subnet, it's not a local subnet, but it's completely a virtual subnet where the nodes are not even in the same physical network or local network. It's in a different networks, but using IP and IP tunneling, we are combining all these nodes into the same network, or rather we are setting up routes which in reality doesn't exist. And just imagine you can on 10.10.8.2 on D2 on this IP or at a particular port, you could be running a proxy server, you could be running a virtual routing software which can route incoming requests to other nodes, other clusters, other internal cluster of computes, and you can do all those kind of crazy things using IP and IP tunneling by setting up virtual routes. So that's the advantage of having IP and IP tunneling, or that is one of the reasons why you would want to use it, right? And again, the connection between D1 and D2, right? Let's say the VPN, let's say the IP tunnel server is running on D2 and the client is running on D1. So the tunnel between these two can be following any IP protocol, which is irrespective of the protocol that the client application C1 and the other server application D2 or D3 would want to use, right? So what I'm trying to say is that, let's say on D2 there is a server called S2, which is let's say listening on port 55551 on 10.10.8.2. Now remember, D1 might be, since the IP 10.10.8.2 doesn't actually exist, D1 in reality will be contacting its public IP, that is 172.40.10.2, but the tunnel software will do the virtual route, and it will make sure that the data goes to the virtual interface or the virtual tunnel interface, which is 10.10.8.2. The other thing that I'm trying to say is that, so let's say the client application C1 and the server application S2 you are using, they are pretty advanced applications and they want to use IPv6 for communication. But on the other hand, let's say your organization, which is distributed over these two networks, you don't right now have the infrastructure to support IPv6 communication. So let's say D1 and D2 cannot communicate via IPv6 right now, but C1 and S2, the client and server applications, they require IPv6. So what you can essentially do is you can create a IPv4 tunnel between D1 and D2, and then let the client application and server application use IPv6 over this IPv4 tunnel. And this is a very common use case. It's called IPv6 over IPv4 tunneling. And you can do the reverse as well. You can do an IPv4 over IPv6 tunneling. That is, you are sending IPv4 packets over IPv6 tunnel, or vice versa. So that's another use case of why you would want to set up IP in IP tunnel, or simply IP tunnels between two networks. Okay, so now that we know what are tunnels and what is its use case, like why we would want to use a tunnel and some of its various applications, let's now try to understand how we can create a tunnel from scratch on Linux. So for this video, for the kind of tunnel that we are going to build today in this video, the approach that I'll be using in this video is using something provided by Linux out of the box, and it's called the TUN devices, or the TUN device driver provided by the Linux operating system. So what we'll be using is TUN devices. To be specific, I'll be using TUN and not tab device. I'll be using TUN device to create our tunnel in this video, and not tab device, but I'll be briefly explaining what both TUN and tab devices are, right? Or rather, what are TUN and tab device drivers in Linux. So Linux provides these two device drivers to allow users to create user space network devices, or rather I should say interfaces, right? So usually when we talk about interfaces like H0 or the Wi-Fi interface, those are directly connected to, either it can be connected to a Ethernet port, or it is connected to your laptop or your machine's Wi-Fi adapter, right? So what it essentially means is, let's say there is a device or a network interface called H0, right? And let's say it has got a IP attached to it, something like 192.168.2.2, and let's say now this interface is connected to your router, right? Let's say this is connected. So basically this interface is connected to your network card's port, and that network card is plugged into your, or basically your laptop is plugged into your router via cable, right? So in short, your machine is connected to your router via your network interface card using cables, or it can be connected via Wi-Fi protocol using your Wi-Fi adapter. And let's say this is the only interface that your laptop has to transmit and receive data to and from your router over your network interface card. So now when, let's say, you want to connect to, let's say, Google, you want to connect to something like Google, what will happen is that your machine will use this interface, because since it is the only interface, it will use this interface to route the packet for google.com to your default gateway, which is your router, let's say, which has a IP like 192.168.2.1, it will send the packet to your router, and the router will then send the packet to your actual host, actual destination via netting, and all those things will come into picture. So what I'm trying to say is that whenever you are sending some packet to the internet or to another host or node or device, it's going over the wire. And from application point of view, no matter what kind of packet it is, whether it's a IPv4, it's IPv6, it's a TCP or a UDP, at the end of the day, on the other side of the Ethernet interface is nothing but physical medium through which it's going. So that's how a typical interface would work. Now what TUN devices allow you to create is user space network devices or interface. So what it ideally would do is it will create a, for example, if I talk about TUN device, it will create a user level network interface which will allow your applications to write and receive data to user level programs, right, and not to the actual wire. From the application's point of view, nothing changes. It's either it's writing a Ethernet frame or it's writing a network packet, that is an IP packet, to the tune or tap interface, as the case may be. But in reality, instead of the packet going to the wire, it's being written to a file descriptor, and from that file descriptor another user space program can read it. So unlike the Ethernet or any other normal usual interface where it's going to the wire, in this case, in case of TUN and tap devices, it's not going to the wire, but the packet is staying at a user space level. If I give an example, the TUN device allows you to, so both TUN and tap device create such user level interface. So TUN device allows you to send point to point packets, or rather IP packets, but the tap device expects you to send Ethernet frames, right, both at user level, not at wire level. So that's pretty much the difference between TUN and tap device. TUN works with IP packets and tap works with Ethernet frames. So now let's take an example of TUN device. So when you create a TUN device or a TUN network interface, it creates a entry in your list of network devices or network interfaces as TUN0, like if you are not providing any custom name. And let's say you can attach a IP to it. Let's say we attach 10.10.8.8, and let's say there is a server application or any application, but let's just go with a server application, application which let's say is listening. It's listening on this 10.10.8.8 on this interface, and let's say at port 8080. So it's sending some response back to this interface, right? Or rather, it's sending some response back to the client that connected to the server application via this interface, which is TUN0 or 10.10.8.8. So for the server application's point of view, it will feel that it's writing this usual IP packets back to this interface. But what's happening in reality is the interface, the device, is actually writing back this data to some file descriptor, which is a user level file descriptor. So the application feels that it's writing back the data to interface, and it's expecting that the data will go via the wire to the actual destination. But in reality, what's happening is the data is simply being written to an FD, and there has to be another program which is essentially the tunnel software or the any custom software, which will actually read the data from this file descriptor, and it will do whatever it wants to do with it. It can send it to the actual client or whatever it wants to do with it. So just if I go over it once again, so if the server sends some data using this interface to the client that contacted it, what it would actually do is it would send the data from its point of view. It will send back an IP packet via this. It will try to transmit an IP packet using this interface. So it's thinking that it's transmitting that IP packet using this interface, or it's writing to the wire, but in reality what's the interface is doing is it's simply spitting it out into this file descriptor, which is user level. And now let's say this client program or this tunnel software, this writes some data back to this FD, right? It writes whatever data it wishes, like IP packet data back to this FD. So what the TUN device will do is it will read this data, it will get this data from this file descriptor, and it will send it back to this server application just as in form of a normal IP packet. So again, this server application will feel that it has received new data in form of IP packet from this interface TUN0, that is 10.10.8.8, but in reality that packet didn't come from wire, but that packet came from a file descriptor to which the tunnel software or some other user level program has written. That's the illusion that TUN0 or TUN devices create. It gives a feel to the server application or the client application listening or connecting to it that the packets it's getting is from the wire, but in reality it's coming from some other user level program, right? That's how TUN devices work. Tap devices is pretty similar, but instead of IP packets, the application, the user level application that's interacting at the interface side of the things or interface side of the tab device, it has to communicate with it using raw Ethernet frames and not IP packets. Again, that Ethernet frames would be written to file descriptor instead of sending it out to the wire. And again, it will get Ethernet frames from FD and give it back to the application that's running. Okay, so now let's see how we can use tune device to create our tunnel, that is our point-to-point tunnel or point-to-point network path between two devices, and how we can, or rather I should say between two applications, a client application and a server application, over a network that is not existing physically, or over a network route that is completely virtual and not real, right? So let's see how we can use tune device to do this, to achieve this. Let me clean all this up. Okay, so what we would essentially first do is create a tune interface, right? So we will use the tune driver provided by Linux operating system to create a tune interface, and let's call that interface. Okay, so before going there, so essentially there will be two nodes. One in this case is in our very simple basic tunnel setup, there will be one node. Let's call it node 1, and that will be the client application, or where the client application will run, and also where the tunnel client will run. So on this node there will be the client application running, and also the tunnel client application that will be running, right? And there will be another node 2, where there will be the tunnel server application running, which is discussed towards our tunnel server, and there will also be the actual server application running. So this is a custom server application or actual application where to which this client app wants to communicate, and the network route or the network subnet that we'll be using between this node and this node for the client app and this server app communication will be something that's not present or configured on any physical network interface, but it will be completely virtual, powered by this tune tunnel that we are going to create. So that's like the setup. Coming to the client, and let's just create a demarcation. So whatever this side is our client machine, and this side is our server machine. So on client machine we will have a interface that is tune 0 interface, and on server machine we will also create a tune 0 interface. So now what we will do is we will have a user application, and let's say this tune 0 interface has an IP 10.10.8.1/24. It's a /24 subnet CIDR, and this one has, let's say, 10.10.8.2, right? So it has got 10.10.8.2/24 again CIDR, and let's say here on this 10.10.8.2 there is a server application listening. Our server app is listening on this IP, and let's say it's listening on port let's say 55555. So it's listening at port 55555. Okay, and now what the client application from here would try to essentially do is the client app will connect to 10.10.8.2 colon 55555. Now the fun part is 10.10.8.2 is not existing on any physical interface on client app, or sorry, on server app, and on client application machine as well. Okay, so now what happens is client app tries to connect to 10.10.8.2, the IP 10.10.8.2 port 55555, and since the IP 10.10.8.2 belongs to the subnet 10.10.8.1/24, that is the /24 subnet we just talked about. So what the Linux kernel would try to do in this case is route this traffic via this tune 0 interface. Since it's the same subnet, packets for all the IPs belonging to this subnet will be routed over or will be sent over this tune 0 interface, which is 10.10.8.1 because it belongs to the same /24 subnet, right? And the moment the packets will be written to this interface, the moment the IP packets will be written to this, will be written or sent to this interface 10.10.8.1, what in reality will happen is all these packets. So let's say client tries to connect to 10.10.8.2, it sends it to here, packet will be sent via this interface, packet sent via this interface. So what in reality will happen is this will get written to a FD, a user level FD. All the data, all the packets that is being sent to this interface for transmission will be written to an FD, and it won't go to the actual wire or the port, the Ethernet port or the interface, because there exists no physical interface called tune 0. So now what we have here is a tune client, or we can call it tunnel client as well. And what it will do is, using normal usual Linux read system call, it will read whatever data arrives at this FD, and this data it will send via socket, usual socket call or usual socket communication. It will send this data to our tunnel server, right? This is our tunnel server application. And mind it, this is a real IP, and this tunnel server is running at a real IP, which is bound to some interface that can be routable between these two actual physical networks. So let's say this is running on some public IP, publicly routable IP, just how I was explaining a while back. Let's say it's running on 172.16.10.2, right? So this is a publicly routable IP, and this can be connected to from this tunnel client, right? So basically this tunnel can open a socket to this tunnel server on this public IP. So what this tunnel client will do is read the data from this FD and send it to this tunnel server application. And mind it, this tunnel server application is completely separate from this server app. This server app or this client app has no idea about this tunnel client or this tunnel server. All it knows is this server's IP, that is 10.8.2. So the client app is only concerned about this server app. It has no clue about the tunnel server in between, or the tunnel as a whole in between. So once this data comes at the tunnel server, what our tunnel server will do is, once the IP packet arrives at the tunnel server, what the tunnel server program will do is, it will simply write this data. Packet goes from here to here. Let's call it packet. That is here also, it's a packet. So the tunnel server program, it will read the packet, it will write it, and you guessed it right, to the FD that is associated with this tune 0 interface. And now, since it's a tune 0 interface, once again, what this tune 0 interface will do is, it will send this data that is written to its FD, tune 0's FD, as a IP packet to this server app. Then the server can process the data, and it can once again try to send it back to the client, which is 10.10.8.2. But once again it will go over this interface, right? It will once again go over this tune 0 interface, because both of these belong to the same subnet. And once again this tune 0 interface will write it back to this FD. The packet will be written back to this FD. This FD, the moment this gets written to this FD, the tunnel server program will once again apply a read system call on this FD, or rather it will keep on trying to read from this FD, and it will be simply waiting whenever some data will be present in this FD. So once again this tunnel server will read data from this FD, which is the packet data, and then once again it will send it back to the tunnel client. The moment the tunnel client has this data, it will write it back to this FD, and once it's written to this FD, the tune 0 interface will provide it back to the client app as a IP packet. And that's how this entire communication happens over this tunnel. This is the actual tunnel, right? This is the actual tunnel. The entire to and fro communication happens over the tunnel, and the fun part is, the client app thinks that it's directly communicating with this 10.10.8.2, and the server app thinks that the data is coming from this 10.10.8.1, which is the source IP of this server's tune 0 interface. But in reality, that's not at all the case. In reality, the data is actually traveling over some other completely separate physical interfaces having completely separate IP. One of them is even publicly routable, but for the client app and server app, they are simply communicating over a subnet which is 10.10.8.1/24, and that's the beauty of IP in IP tunnel system. So the client app and server app can very well be communicating over UDP, and the tunnel in itself could be using TCP or vice versa. So the tunnel here could have been very well be using IPv4, but the client app and the server app could have been using IPv6, and all those things could have been tried, and all those separate combinations can be tried out. So that's the use case of this kind of IP tunneling system, and that's how we are going to use Tune device to create a tunnel in this video from scratch. So now that we have some idea on how an IP tunnel works using Tune interface or a Tune device, we will try to code it from scratch, and we will try to spin up a VM, and then we will try to communicate with that VM over this imaginary route which doesn't exist in reality. So let's see how we can do that. Okay, so now before we start with our implementation, there are a few things we need to notice in this design. So the first thing, if you look at this tunnel client and tunnel server at both ends of the design, let's just call them tunnel program at this point, and in both the cases the tunnel program is doing one very specific thing, right? On one end it's reading from the FD and it's writing to the tunnel server. I mean, writing to or sending data to a server or something like that. When I say it's sending the data to tunnel server, is what I'm pretty much doing from a Linux point of view is I'm opening a socket to this, or I'm connecting to this. I'm pretty much connecting to this tunnel server via socket, which gives me a socket FD, right? It gives me a socket FD, and then I'm pretty much writing the data that I'm reading from this FD into that socket FD, so that the data goes to the tunnel server. That's how just normal sockets work, right? You connect to a server socket, you connect to a server IP port, that gives you a socket FD, and you write to that socket FD, and that's how data is transmitted. And again, when you are connecting to a server from server's point of view, the server is pretty much getting a connection socket FD, right? So the server would read from that connection socket FD, and as well as when it wants to send back some data to client, it will write to that connection socket FD. So if I just reiterate what I just said, so when the tunnel client wants to read something from the Tune 0 FD, it reads from this FD, and when it wants to send that data to the tunnel server, it simply writes to the socket FD of this tunnel server. So it reads from one FD, writes to another FD. In one case, in one side it's the tunnel FD, on the other side it's the socket FD, and that's when it's sending the data to server, and when it's receiving data from server, it reads from the socket FD and writes to this tunnel FD. Now if we check this tunnel server, what's happening in this tunnel server is it's pretty much the exact thing. When it's receiving data from the client, it's reading from the client FD and writing to the tunnel FD, and again when it wants to send some data to the client, it reads from the tunnel FD, it reads from the Tune FD, Tune device FD file descriptor, and it sends to the tunnel client's connection FD. So in both cases, the tunnel program is reading from one FD and writing to another FD, and vice versa. So it's essentially the same program, right? Because server socket and client socket works in different ways. In case of a server, there is a concept of listening and binding, and in case of a client, there is only a concept of connecting. We can use the same program in server mode as well as in client mode, only how the socket is operating will change. The other very important thing we need to know is, since it's a duplex connection, since it's a two-way connection, data can arrive at any point of time on the Tune FD as well as on the socket side FD, right? So at any point of time, we must read from Tune FD, write to socket FD, and we should read from socket FD and read to Tune FD. This should happen continuously, right? It can't be like first I read from Tune FD to write to socket FD, then again I read from socket FD, then again I write to Tune FD. It can't happen like that. At any point of time, I should always be reading from Tune FD. If there is data, I should be writing it to socket FD, and on any point of time, on any point of time, I should always be reading from or trying to read from socket FD, and if there is data, I should write it back to Tune FD. So that two-way flow of data should always be happening, or at least the tunnel program should always keep on attempting to read from a Tune FD as well as from socket FD and then exchange the data, right? So one very common way people usually tackle this problem is using select library call or epoll system call in Linux, right? It allows you to poll file descriptors, and keep on polling until data is available. Once data is available, you can send the data to or write the data to another, the second file descriptor. So one way is doing this sort of epoll or select, or using this sort of epoll or select library call, and the other way is the old classic way, is you, for just from the perspective of one tunnel client or tunnel server, that from the perspective of one tunnel program, you do the reading from TuneFD and writing to socketfd as part of the main program, and for reading from socketfd and writing to TuneFD, you spawn a process, or vice versa. Basically, you fork a process. So let's say the main program will take care of reading from TuneFD and writing from socketfd, and the forked process will take care of continuously reading from the socketfd and writing to the TuneFD. So that can be another approach. So since I've already made a video on process forking in Linux, something that I have already discussed in past, in this video I'll go with how we can use a separate process to. So in this video I will go with the process forking approach. So I will do one of the communication. So I will delegate one side of the communication to a new forked process, right? I might discuss, again, epoll system in Linux is an extremely efficient and pretty cool system, and I don't want to include that concept in this video, or I don't want to play around with it in this tunnel video. So what I would do is I would rather create a separate video on it and make something different to explore the epoll concept or the select library call. Again, epoll and select library calls are different, but most probably I'll explore epoll in a different video. So yeah, let's see how we can implement this entire design using a C program. Okay, so now that we know the basic design of our tunnel program or our tunnel system, so now let's start implementing it using C. So again, I won't be using any external library for this. I'll only be using the tunnel device driver or the tune tab device driver that's provided by the Linux operating system, and I'll be building everything on top of that. So as always, first I'll start with importing some libraries. So let's quickly get it out of our way. Okay, so we are pretty much done with all our imports, and let's define some constants now using hash define. So first I'll define buffer size. This I'll be using when reading and writing to file descriptors. So these two, mode tunnel server and mode tunnel client, these are just to specify tunnel program is running as a server or as a client. So this will be configuring via command line arguments. Accordingly, we'll use this value to denote whether this program is running as the tunnel program is running as a server or a client. So this is the port on which the tunnel server will be running. If the program is running as a server, then it will be listening on this port, and if it's running as a client, then it will try to connect to this port on the particular tunnel server IP. And finally, a macro to handle errors. Let's define some more variables. This is again the buffer for reading and writing. These are the, remember there will be two file descriptors, one for the tune device and another for the socketfd or the socket. So these are the two file descriptors, netfd for socket and tunefd for the tunnel. So remote IP will be used to store the server IP to which the tunnel client will be connecting if the tunnel program is running as a client. Tune IP is in order to store the new virtual IP that we'll be creating. We could have directly used the macro, but I'm just storing it in a variable here. These are usual socket ADDR variables for storing local and remote addresses. So remember, I just mentioned that we will continuously be reading from the tune FD and writing to the socket FD, and reading from socket FD and write to the tune FD. Since both the things have to be done simultaneously, one can happen in the main program and the other can happen in a fork process. So in this case, the reading from tune FD and writing to the net FD or socket FD thing, I'll be doing in a different process, and reading from net and writing to socket, that will be happening as a part of the main program. So the first thing now that we would want to do is allocate the tune interface, or rather create the tune interface, right? So let's get that done first. So creating a tune interface is pretty easy. It has a way of its own, or a process of its own, which we just need to follow. So the kernel provides us with something called /dev/net/tune. This is called the clone device. So this is our entry point to the tune tab device driver. So in order to create an interface, what we need to do is open this clone device file, get a file descriptor to it, and then apply a IOCTL call on that file descriptor to create the tune or tap interface, whatever we want. So in this case, we'll be using the IOCTL call on the clone device file descriptor to create a tune interface. So let's see how we can do that. I'll call the function create tune if or interface. So in case I want to give it a custom name, that's why I'm taking this parameter called it's a string called dev. If you do not provide any name while creating the tune interface, the kernel will give it a default name. So for example, the default name that the kernel gives your tune device, if you do not set any custom name, is tune 0. The next thing we will have is something called flags. So these flags will be used while calling the IOCTL call, and this determine the configuration of the device that, or the interface that you are creating, right? Whether it will be a tune device or it will be a tab device, and things like that. I mean, whether it will be a tune interface or a tap interface and things like that. There are various configuration options when you are configuring your tune tap interface, and there is a whole list. You can always check it out on the internet. But for now, our use case is pretty much simple. We just want to make sure that it's a tune interface that we are creating. And this is the device file I just mentioned. It's called the clone device, and now we'll attempt to open it. We'll initialize the IFR struct. Okay, so what all we did is we created our IFR struct here, and we attached the flags to the IFR flags parameter, right? And as I just mentioned, this flag will contain whether we want to create a tune interface or a tap interface. And if we have provided a custom name for our interface, for our tune interface, then we use that and we copy that name to IFR underscore name parameter using strcpy. And finally, we are going to make the IOCTL call, and here the second parameter that we will provide is something called tune set if. This simply means that we are setting the configuration for the tune device, and we are not fetching the configuration and name, but we are setting it. That's what this parameter means, or this constant means. So you can check it here. It's simply a macro. So we are setting our tune interface, and the other thing that we will do is we will pass the IFR struct which contains the configuration, and we will do some error handling. If the IOCTL call failed, we will simply close the FD and exit with an error. And finally, what we'll do is we'll copy to the dev buffer that we provided the name of the interface. We do this in case we have not provided any custom name and the kernel comes up with a new name, and simply we can copy that name to the buffer that we provided, so that we know what name the kernel set for our tune interface. And that's pretty much it. We create the interface and we get back the file descriptor in order to write things to the tune interface. However, just by creating this interface, it won't do us any good, because this interface has got no IP attached to it right now. So what we need to do is we need to create the IP, and also we need to attach an IP to this interface, and also the interface, we need to bring this interface up. And for that, we could have also used C. We could have done it natively using C, using the desired structures and system calls, but since that's not the main focus of our video, it's a thing in itself. Like, we need to use certain structs, we need to set them, we need to again do certain system calls to set the IP to the interface and bring it up. Since that's not the main focus of our video, and I don't want to spend much time on that, what I'm going to do is I'm going to take help of the classic or the usual IP command, right? And how I will call the IP command is I'll simply call shell commands from within this C program using the system function call, right? So in a moment I'll show you how to do that. So I'll create a function called set up tune device, and what I'll get here is the first parameter will be the CIDR, IP CIDR, remember the 10.10.8.21 thing, and then the interface name, and then I'll just create a holder for the link up command. Shouldn't be more than 64 bytes or characters. Then set addr command, then I'll take help of sprintf, very nice and very powerful library call to create the commands. So the destination buffer will be, right now I'm creating the command to bring up the interface, so that will be IP link set percentages, the name, and nothing but up, and I'll provide here the name, and again I'll do the set addr command. I'll create the set addr command and I'll do IP addre. Oh, I need to provide the IF name as well. So these are the usual IP commands, right? So I'm adding a CIDR to a interface name and I'm bringing it up, and finally I need to execute them. So for that I'll do system link up command and system set addr command. So now I'll create two very tiny helper functions, one to read from OFD and one to write to OFD, and we'll be using both of them in a moment. So first I'll do int read from FD. I'll take a FD, the buffer, and the number of bytes it wants to read from the buffer, from the FD into the buffer. So I'll do something like nread, and nread equal to read FD comma buff comma n. If nread is less than 0, that is it's an error, then I simply exit with error, failed to read data, and I will return the number of bytes read, and then I'll create int write to FD, and once again there will be a n write, or maybe n wrote, yeah, whatever, I'll just call it n write. And if n write equal to write FD comma buff comma n, again if it was not able to write anything, then we simply exit with error, failed to write data, and return n write. Now we have our two tiny helper functions, one to read from file descriptor, one to write from file descriptor, and both of them will take a FD, number of bytes to write, and a buffer. And so now I'll create two more wrapper functions using these two functions. So the first one is copy data from the net FD or socket FD to the tune FD. So it will simply read from the socket FD and write to the tune FD. So let's do that. So once again I'll have two variable to track read and write, and remember we have to do it continuously. We cannot take any pause. We need to keep on reading and writing. So yeah, so in an infinite loop what I'll do is n read equal to read from FD, the net FD, and remember I just created global variables net FD and write FD, and so I don't need to define it inside the function or take it as a parameter. And I will give buff size if nread equal to 0. If nothing is read, I'll simply continue, or else I'll just do it for logging purpose. I'll say read d bytes from socket FD and read, and write equal to, now I will write to the tune FD, tune device FD, and the number of bytes that were written, and that's pretty much it. So that will simply read from net FD and write to tune FD, and it will do so continuously, and we'll create a similar function which will do the reverse. Let me quickly do that as well. Tune copy tune to net, it will simply do the reverse. Actually we could have combined both of these into the same function, but just for simplicity I'll keep them separate. And what I want to do is this tune to net function, I want to run it as a part of a separate process, and so whenever this logs anything out to the terminal, I also want to print the PID from which it is coming, so that we can know the PID of the child process, and we can differentiate when the main program is writing and when the child program is, or the child process is running and writing something to the logs or to the terminal. So what I'll do is I'll get the PID of the process, and once again I'll start the loop. I'm doing the same thing again, but this time instead of reading from netfd, I'm reading from the tunefd. If n read equal to 0, once again I'll continue, and then I'll simply print, and this time the first thing I'll print is the PID, and then the same thing, read d bytes from tunefd PID slash n read. And then I'll write it. Once I've read it from the tunefd, I'll write it to the netfd. Wrote percentile d bytes to socket fd PID and n right. That's it. So that's our two functions for reading and writing, that is copying data between tunefd and netfd. So we are pretty much done with our ancillary functions or our helper functions and the function to create the tune interface. And next what we are going to do is we are going to stitch everything together and create the sockets and start with our reading and writing loops. So let's do that. So now I'll create my main function. I'll be taking a lot of inputs from the user, so for that I'll be using get long ops actually. By default I'll set the mode to be client. Sock opt is just to set SOD use ADDR to enable SOD use ADDR on the socket. You might want to do it if you want to, while you are testing, so that you can easily reclaim the address you were listening on earlier when you kill the program or something like that during testing. And what I'm going to do is I'm going to create the struct that will be used by getops. Just bear with me, we will have quite a few options. So typically the options that we would let the user to provide us is whether the tunnel program will be running as a server or a client. The IP of the tunnel server, if it's running as a client, it must have this parameter set so that it knows where is the tunnel server running so that it can connect to it. Next is the port. If it's running as the tunnel server, then it will be listening on this port. If it's running as a tunnel client, then it will be connecting to this port. Even the same for IP actually. So if it's running as a tunnel server, then it will be listening on this IP, or else it will be connecting to this IP and port. Then the tune IP. The tune IP is pretty much the IP that will be configured on the tune interface using the system library calls that I just showed. And that's pretty much it. So next, let's just get and parse these arguments provided by user. So again, I'll be using get opt long. So that's it. We have now all the user options stored in their respective variables, and now we can start with creating our sockets. So before that, let me just put some debug logs or debug outputs. so that we know we have got the correct options. So if mode equal to mode client, then I'll simply say that it's running as a client. And also where the server is running. Actually, we won't be using remote IP if it's running as a server. We only need it to connect to it when running as a client, because when I'm running as a server, I would rather prefer listening to all the interfaces. So I'll just use a 0.0.0.0 when I'll be creating the server. I'll just show you in a moment. Server running at port %LD port else printf running as server on port. So yeah, when it's running as server, we'll simply show the port. So as I mentioned, for server listening on port, so as I mentioned, we'll be mentioning only the port because we'll be listening on all the interfaces. Okay, and that's that. And simply now I'll spit out the tunnel IP as well, or the tunnel or the tune interface IP actually. That's it. Now we have all the options parsed, and we have put our debug outputs or debug logs, and now we can start with the actual socket creation. So now let's allocate or create the tune interface, which will give us the tune FD as well. So let's do a tune alloc if name iff. So we want it to be a tune interface, and we will pass another flag, which is iff nopi. I won't go into details of what is iff nopi here, but I'll just use it for now. And then I'll do, if everything worked out fine, I'll do tune device created, setting up interface, or let's call it tune interface created. Yeah, I'll do a \n tune IP and if name for setting up the interface. Now I'll do sock fd equal to, I'll create the socket. It will be an internet type socket, and I'll be using TCP for the tunnel. So basically the tunnel will be using the TCP protocol to transmit data. You can use UDP as well. And if just another quick error handling, if socket fd is less than 0, exit with error, failed to init socket. And I missed a I here. Now starts the distinction between tunnel client mode and tunnel server mode. So if mode equal to mode underscore tunnel client, then we memset, then we first, as usual, we initialize our socket address struct. Remote is nothing but our, both local and remote is nothing but socket ADDRs, like socket ADDR instructs. So we simply initialize it first. Size of remote. Now remote dot send family equal to AF inet. Remote dot send ADDR equal to dot SADDR equal to inet ADDR remote IP and remote dot syn addr equal to h tons port. So it's just simple socket setup, like nothing fancy is going on here. We are simply setting the socket family, socket address and all those things for the remote address, the IP port and those things. And this I believe is remote, it will be syn port. Okay, so again I have explained what is htons in a few of my previous videos. It's like basically converts byte order from host byte order to network byte order, because when you are working with numeric values in network structs, the byte order should be network byte order, and network byte order is always big endian, and host byte order can vary between big endian or little endian, right? So htons takes care of that conversion from byte order, from one byte order to another byte order. So once we have this, what I'll do is I will try to connect to the server IP or server address. So if the return value of connect is negative, we simply exit with error and we say fail to connect, and then we do a printf connected to server, sockfd. And since the TCP handshake and connection has been done with the server, we can initialize our netfd with our socket FD, because when it's running with in client mode, this socket FD using which we connected to the server becomes our netfd, right? So netfd is just a variable name we are using for the socket file descriptor. And otherwise, if it's running as server, then what we do is we first set our socket option of making the socket use SOD use ADDR so that we can reclaim addresses. So now you know why I defined that variable sockopt and set it to 1. And finally size of sock if that's less than 0, we simply once again exit with error saying that failed to call set sock. So once again, and now I'll initialize the local sock ADDR in. So basically I'm now setting up the address on which the server will listen, or the address struct on using which the server will listen. Local.send family equal to ef inet dot send addr dot s addr equal to h tunnel in. So here we are specifying that we want this server, the tunnel server, to listen on all the interfaces available. On Python you would have done something like listen on 0.0.0.0.0, but C provides you with this macro which is inaddr any, and which is pretty much all zeros. Then what we're gonna do is that we'll set the port, and once again we need to do htons and provide the port. And now we are going to do the typical server thing, that is binding the socket to the address that we just came up with. So we bind it to struct sock addr failed to bind socket, just another error message. And so if bind socket free struct socket adr star local size of local less than 0. Yeah, that's pretty much it. And then what the immediate next step of binding is you start listening on that address, and I do socket fd5. So 5 is the queue of pending connections. If we are not able to listen, then we exit. So now what I'll try to do is I'll try to accept connections on the server, and once I get a connection, I'll store the connection socket FD into the net FD, because we'll be using this FD to communicate back with the client. Simple client server communication. So for that, what I'm going to do is first I'll define the size variable of the remote address struct. Then I'll initialize the remote address struct, and then I'll try to accept connections. So just another error message in case accept fails. And then simply I log that I have received a connection. That's it. So now we have, in both the cases, whether it's a client or it's a server, we have the netfd initialized. So in case of client, it's a netfd set to the socket fd using which we are connecting to the tunnel server. In case of server, netfd is the fd which we are getting from accept when we are accepting a connection from the client or from any client, right? So now since we have both the fds ready, both the tunnel fd and both the tune fd and the socket fd, we can now start the two-way communication. So let's fork our process, which will read from tunefd and write to netfd. I'll use the usual fork library call, and now the first thing I'll check if it errored out, which I hope it shouldn't, but nonetheless, fail to fork child. And then if fork val equal to 0. So if I'm inside the child process, then I'll call copy tune to net, which is a function that will read from the tunefd and write to the netfd. Else I will call copy net to tune, which will read from the netfd and write to the tunefd. And that's pretty much it. That's our tunnel in 231 lines of code. There are some more issues. Let me fix those. Yeah. So now let's try to run it and test it by doing some communication between a client program and a user program over our created tunnel. Okay, so first things first, let's try to see if the program compiles. So for that, I have already made a makefile here. It's the same usual makefile that's got a build, run, build and run, and clean. Although I guess we'll only be using the build recipe, because for running it we'll be using several command line arguments, as we have already seen. So let's try to compile it. It looks like there are some issues. Let's fix them one by one. So this function name is create tune interface. So let's call it, I believe I have used the wrong function name to call it. So let's call it create tune if, and the other thing is strcpy. Again, I believe I have did something wrong here. Okay, I see what happened. It should have been strncpy, since I am copying only this many bytes from the dev to IFR name, because this is the max number of bytes I can copy, or that can be the length of the IFR name. So let's try to copy build now, and it worked, and the binary has been produced, which is TUNL, or tunnel in short. So now let's try to test it. Now how do we test it? We need one more node, right? And for the second node, where the tunnel server will be running, we'll be using a virtual machine, a VM, and I'll be using good old virtual machine manager to do that. So I've already created a VM using virt manager, and that's running on, if I do IPA, the virtual machine is running on this subnet 192.168.122.1, right? And yeah, that's pretty much it. And the virtual machine in itself is running on 192.168.122.190. I can show you right now. So if I do 19 SSH on 192.168.122.190, and the username is Ubuntu. So here's my tiny virtual machine, right? So now what we are going to do is we are going to transfer a copy of this binary that we created. Sorry, let me exit. Binary that we created to the virtual machine. So there will be 4 things running at the same time. The tunnel server will be running on the virtual machine, and it will be listening on all the interfaces, just as we discussed. Let's say it will run on port 55555. So we have anyway set the default port here to tunnel server port, which is 55555, but we can change it from command line argument as well. So we can run on any port on the server, but let's say the tunnel server will be running on port 55555 as of now. So that's one thing that will be running. And so on the local machine, the tunnel program will be running on client mode. On local machine, there will be another program running, that is our actual client, which would want to communicate with some server program which is running on, let's say, a tune interface 10.10.8.21 server. And on our local machine, the tune interface would be something like 10.10.8.1, right? And then what we will try to do essentially is we will try to communicate with the IP port 10.10.8.2, let's say port 55551 on server, from interface 10.10.8.1 on local machine, right? And as can be seen from the output of IP command, right now there is no 10.10.8.1/24 subnet present, right? These are all the interfaces I have, but none of them is a tune interface with or none of them has a IP called 10.10.8.1/24 attached to it. And same on Ubuntu, I can show you that as well. As in Ubuntu VM, I can quickly show you. So let me do one thing. Let me divide the screen. So since we'll be running 4 things, so let me just create. I'll just minimize. I hope this much it should be fine. This much it should be visible. And let me just divide the screen into 4 parts. It might be a bit difficult to see, but I need to have four things running at the same time. So hence I have to divide it. And on these 2 screens, what I'll do is I'll log into the VM. So it was 122.190, I believe. Yeah. And the other one, I will do the same. Let me quickly copy paste. And there we go. So now we are on these 2 screens. We are inside in these, like the right top and bottom terminals. We are inside our VM. On the left bottom and top terminals, we are in the local machine. And the first thing I would want to do here is create a directory. Let's call it same TUNL maybe. And let me get inside it. So it's home Ubuntu tunnel, and what I'll do is I'll just SCP the binary from here to the virtual machine. Okay, so I believe it's here. And now what I'm going to do is I'm going to start the tunnel server to create a tunnel. So once again, even here no 10.10.8.2/24 interface is there. Let's see what happens when I start the tunnel server here. Not only I'll be starting the tunnel server, but I'll also be creating the tune 0 interface here, right? Because that's the interface where the actual server application will be running and which will be processing the client, right? So the tunnel server will simply be proxying the data to that tune interface, where it will be further sent to the actual server application via FD. So let's start it now. For that I'll do tunel -s because it will be done as the server. I won't provide any port because I want to run the server on 55555. I mean, I want to run the tunnel server on 55555, not the actual server. And the other thing I will do is I will provide the tune 0 interface IP, and as I mentioned, I'll call it 10.10.8.2/24, and let's see if it works. Okay, so thing is, the kernel won't allow you to create a TuneTap interface without using the capnet admin if you don't have the capnet admin. One way to do it is using sudo, because once you run it using sudo, you automatically will possess the capnet admin capability. So let's do that. And it says tune interface is created, setting up interface, and tunnel interface IP that is being used is 10.10.8.2/24, and it's listening on port 55555. And let's see if it's indeed listening. If I do IPA now, and here we have it. We have a new interface. Let me try to just expand it a bit. We have a new interface called tune 0 interface, right? It's a point-to-point interface because it's tune, not tap. It's up, and the IP attached to it is 10.10.8.2/24. Cool. We have successfully created a tune interface, right? As you can see, it's now waiting for new connections to be received. So now what I'll do is, and again, just to verify things from my local machine, let's try to do a ping to 10.10.8.2, and I cannot, right? Because for local machine 10.10.8.2 is non-existent. That neither the IP exists, neither the interface exists, neither there is any existence of this IP 10.10.8.2, and neither there is any route to reach this IP 10.10.8.2. So for local machine, it's completely non-existent. It doesn't know about this IP. Now what I'm going to do is I'm going to create or start the tunnel client program, and basically the tunnel program as client on my local machine, and that client will connect to the tunnel server. So let's do that. Tunnel -c because it's client -I 192.168.122.190 -port. We don't need the port. I mean, by default we have set it to 55555. And finally, the other thing that I'll be providing is the tune interface IP. So that will be, in this case, 10.10.8.1/24. We need to keep the subnet same, and let's start it. Okay, same problem. I need to do a sudo, and the connection has been made, received connection, and it will do the initial handshake of like creating the connection. And if you see that now the child process has also been spawned, here also a child process has been spawned which will do the to and fro thing. So basically one process will the main process will read from netfd and write to socketfd, and the child process will read from tunefd and write to socketfd, right? So now, since the tunnel has been established, we can now my local machine be aware of 10.10.8.2. Is it possible? Can I get a ping from 10.10.8.2? Let's try 10.10.8.2, and it works. I'm getting a ping, and you can see that the ping packets are being sent to this 10.10.8.2 via the tunnel. So in both the cases, you will see here you are getting the logs, like it's reading from the in this case it's reading the ping packet from the FD, the tune FD, and writing to the socket FD, and in this case it's reading from the socket FD and writing to the tune FD, the moment the tunnel server writes the ping packet, or rather the ICMP request packet on the tune interfaces FD, on the receiving side, the ICMP packet goes to the kernel processes the ping ICMP packet and it sends it back, right? So now we know that ping works and our local machine is able to contact 10.10.8.2, so our tunnel is working fine. So now let's do something interesting. What I'm going to do is on 10.10.8.2, that's on the server, I'm going to create a simple netcat UDP echo server, right? So let's do that. So I'll do nc -u -s 10.10.8.2 and -p is, let's call it 55551. Okay, I guess I did something wrong. I had to do actually -l because I'm going to listen, and it has started to listen, right? And now what I'm going to do here is, my tunnel is still running, by the way. So now what I'm going to do is I'm going to do a nc -u, and then I'm simply going to connect to 10.10.8.2 and port is 55551. And let me just make some space here. And I have started the netcat program, the client and the server on both the sides. And now let's see, let me send hello. And the netcat server on the virtual machine is able to receive whatever I am sending from the client side. So now it should be clear what I meant when I was saying the actual server. The actual server is this program that maybe some developer has developed, anything like, which is listening on this interface 10.10.8.2, the tune interface. And this tunnel server is just the tunnel server which is doing the proxy part, like the tunneling part. So now what I'm trying to say is that although our tunnel is using TCP, but our client and server, the actual client and server applications are connecting to or communicating to each other using UDP. The tunnel is not at all bothered. It doesn't even know what's being sent or what's being received. It's just taking the network data, putting it inside a TCP packet, and it's just sending it to the server, right? And vice versa. This entire communication is happening over UDP between the client and the server. You can write something here as well. Hi, this is server. You can write hello, this is client. And this entire thing is happening over the tunnel, and it's happening over a IP which doesn't really exist, like a subnet which doesn't physically exist. It's just a user space interface that we created, and the rest of the thing has been taken care of by the tunnel, right? And so that's the beauty of tunnel program. It lets you create interfaces, it lets you create routes which doesn't actually exist, right? And also it lets you encapsulate packets of one protocol into the packet of another protocol. So that's IP tunnel for you. And you can also see the child process is working fine, the main programming is working fine. We are getting the logs, how many bytes read, how many bytes written. So whatever it's reading, it's writing the same, and same on the server as well. So it read 48 from socket, it wrote 48 bytes to tune device FD, and so on and so forth, right? And the ping also should work both ways. So if I do a ping 10.10.8.1, it should work, right? You are pinging an interface which doesn't physically exist. It's a user space interface. So that's it. That's what I wanted to discuss in this video. That's what I wanted to build in this video, or a small tiny tunnel program to create a tunnel between two devices using IP in IP tunnel and using Linux TUN device and device driver from scratch. So yep, that's it for this video. Hope you all liked and enjoyed it, and see you all next time.